Section 3.1 is about symmetry, and in this chapter we're going to look at a lot of properties of graphs, and we're going to improve on our graphing abilities and help us understand functions and their graphs and a lot more. And this is going to help us solve many problems to come in this class. Just don't be scared of graphing. Graphing is not hard. All right, so first thing we have here, symmetry, point symmetry. You can plot some of the graph and use symmetry to graph the rest. So a lot of graphs have symmetry. They follow a specific pattern. A figure with point symmetry can be turned about a center, and in less than a full turn, the image is the same. So if you notice here, this first I have the letter Z here, all right? And if I rotated about this point M, if I rotated everything, if like I took like this was a knob on the top or a lid, and I spun it this way, right? If I turn this thing, this point would end up being the bottom of my Z, and this point would rotate and end up being the top of my Z, and we still have the same figure. So in less than a full turn, this top line right here went from here to right here. It didn't go a full 360 degrees, it went 180 degrees, right? So in less than a full turn, I still get my same shape. And keep in mind, I noticed that this bottom part of the Z is way bigger than this top, and that's just me being a bad drawer on Microsoft Word. Those are meant to be the same side. So this has point symmetry. As long as I can turn it in less than one full turn, it has point symmetry. All right. In the same case, this line has point symmetry. All right. On the point M. If I were to turn this way, it doesn't matter, clockwise or counterclockwise, say I turn this thing this way, all right, this portion of the line here would become this portion of the line, and the same part, I'd take this, and it would turn and become all the way over here. All right, so in less than one full turn, in 180 degrees, I spun that thing, and it was still the same shape. Again, the same thing, obviously, for an oval over here on my other one, and that would be the origin, and the origin is a very common place for symmetry on our graphs. All right, so if I took this and spun it along the origin, all right, if I flipped, say here, and spun it along the origin, it would go ahead and end up right there. In less than a full turn, I would still have an oval. All right, so that's a little introduction into point symmetry. All right, so I told you that the origin was really common, so we're going to focus right now on respect to the origin. A function f of x has a graph that is symmetric with respect to the origin if and only if, when we plug in negative x for x, we change all of the signs in our graph. All right? Or if we have a point AB in our graph, there has to be a point negative A, negative B also in that point. So what I mean by that, and I'll show you by this graph right here, it says graph 1 all over x. Well, 1 all over x, you'll come to find out, is a very common graph, and hopefully you had it quite a bit in Algebra 2. All right, but 1 all over x graph looks like this, and then on the other side it looks like this. And if you weren't sure about that, you can always plug in points. If I plugged in 1, so if I plugged in 1, 1 all over 1 is 1. I had a point 1, 1, right? If I plugged in 2, I would get 1 all over 2, which is 1/2, all right, which would be down here. It gets smaller and smaller and smaller. Now, again, if I plugged in -1, I would get 1 over -1, which is -1. 1, -1 down here. And if I plugged in -2, I'd get 1 all over -2, which would be -1/2. This graph is symmetric with respect to the origin. If you notice, if I plug 1 in for x, I get 1 for y, right? That's this part, 1, 1. If I plug in 1, 1, if that is a point on this graph, in order for this to be symmetric with respect to the origin, would be that the graph of this negative x, so -1 and -1, would have to be on the graph. We find out that that's true. Right, in the same sense, look at 2. All right, since I've put the point 2, 1/2 is on my graph, right? In order for it to be symmetric respect to the origin, This is saying that -2 and -1/2 would have to be on the graph as well. So -2 and -1/2, are those also on the graph? Yeah. All right. And again, 1 point can't show symmetry, and 2 points can't show symmetry. This is saying if I plug, my first definition is saying is if I plug a -x in for every x that I see and it changes all the signs, then it's symmetric with respect to the origin. So if I have f of x equal to be 1 over x, and if I plug in f of -x, so anywhere I see in x, I'm plugging -x, did that change the signs of all the ones in my graph? Yeah. Well, another example of that would be like x cubed plus 2x, all right? That's f of x. If I plugged f of -x into that, I would get -x cubed plus 2 times a -x, all right? A negative cubed is still a -x, so I have -x cubed, and 2 times a -x is -2x. Notice how this changed, the sign in front of here changing from a positive to a negative sign, and a positive here to a negative sign here. That's symmetric with respect to the origin. All right, so I've shown that in a couple different ways. I hope that makes sense. All right, so here we are. Determine if f of x equal to 5 and g of x, or sorry, x to the 5th, and g of x equal to x to the 6th are symmetric with respect to the origin. All right, so again, I don't know, we could pick a point. 1. When I plug 1 in, I get 1. So if 1, 1 exists, in order for it to be symmetric, I'm looking at f of x right now, by the way. In order for it to be symmetric, if I would have to have the point -1, -1 would have to exist in order for it. So we said that if AB exists, then -A, -B had to exist. All right? So if I plug -1 into this, -1 for my x value, -1 to the 5th power is still -1. Anything to the odd power doesn't change it. Will still make it a negative, doesn't change it to a positive. So -1, -1, that does exist. All right, so far we're thinking it's symmetric with respect to the origin. All right, in the same case, if I plug in A for f of x, if I plug in, sorry about that. If I plug in another point, if I plug in 2 to the 5th power is 4, 8, 16, 32 is 32, right? If I plugged in -2, I'd get -32. All right, and this would continue to fall around and continue to be true. This is symmetric with respect to the origin. All right. Now what about g? All right, g of x. Well, let's take 1 point. Let's take 1, 1. If I plug in, sorry, scratch that. Let's take the x value 1. When I plug in 1, I get 1 for a y value. 1 to the 6th power is 1. So in order for it to be symmetric with respect to the origin, -1, -1 would have to exist. It would have to exist. If it doesn't exist, it's not symmetric with respect to the origin. So I'm going to plug in -1, and for it to be symmetric with respect to the origin, I'm going to have to get -1 for my answer. -1 to the 6th power. Well, you can type in your calculator and you're going to get a +1, or you can think -1 times -1 times -1 times -1 6 times, and you know it's an even amount of negatives, so it's going to be a positive. Therefore, this is not, g of x is not symmetric with respect to the origin. X to the 5th is. All right. Now on to line symmetry. The graph can be folded along the line and it mirrors the other side. They can be symmetric to the x-axis. The ones we're going to look at, the x-axis, the y-axis, y equal to x and y equal to -x. But if you think about any line, I can show you a very typical graph, a parabola. I know you've dealt with these in Algebra 2. All right, and if you pretend here that the y-axis is a line on a paper and you could fold that thing and fold it across, say this green side here. If I folded across this line, this green side would land exactly on the other side. All right, so that would be symmetric with respect to the y-axis. And in the same way to the axis, say we had a graph like that, right? If I were to fold it along this x-axis line, all right, it would land right on top of here, or this side would land on top of that guy, right? All right, so that's what line symmetry means, all right? And here I'm giving you a few more definitions. If it's symmetric with respect to the x-axis, if I plug in a value for x and get another value for y, it's symmetric to the x-axis if I plug in that same value for x and get the negative y. So notice the x values are the same, and in the case that where I can get a positive and a negative. The easiest example I can give you is, what if I give you y equals the square root of x? And they're asking you, is that symmetric to the x-axis? Well, let's plug an easy root. Well, let's plug x equal to 4. When x equals 4, y can equal 2, or y can equal negative 2. So we have a point for 2 and a point for negative 2, right? Because when we take the square root of everything, it's plus or minus. So that would fulfill this requirement here, that when I plug in the same x value, I can get both a positive and the negative. Therefore, it's symmetric with respect to the x-axis. The y-axis, all right, is saying if I plug in an x and I get a y, all right, if I plug in the negative value of that x and get still the same y, it's going to be just symmetric with respect to the y-axis. So the easiest one I can give you is a parabola again, like this. All right, and the graph or the equation of a parabola is y equals x squared. All right, if I pick 2 for x, I get 4. And this says, all right, so it is a negative of 2. Does that also get you 4? The same b. Well, negative 2 squared is 4, so therefore it's symmetric to the y-axis. And again, one point doesn't prove symmetry. We could also look at it this way. If I plug a in for x, a squared, right? I get y equals a squared. So if I plug in y equals negative a squared, all right, I get a y equals a positive a squared, because negative a times negative a is a positive a squared. All right, so I got the same answers here, therefore symmetric to the y-axis as well. Okay, so example 2 here, I'm going to leave this up here. Determine whether the graph f of x equals x to the 4th plus 3x squared plus 8 is symmetric with respect to the x-axis or y-axis. Neither or both. Well, the first thing I did for us, if I took a graphing calculator and I graphed it for us so it could save us some time. Obviously, if you look at the graph, is that going to be symmetric over the x-axis? Well, probably not. All right, since we can't fold it over the x-axis and still get the same graph, we can probably eliminate that right away. And I can show you a reason why. Well, it says the x-axis, all right, if I plug in, say, 1, all right, 1 to the 4th is 1 plus 3 times 1 squared is 3, so I get 1 plus 3 plus 8, I get 12, right? If I plug in negative 1, or sorry, if I plug in 1 again, anytime I plug in 1, I'm always going to get 12. I'm not going to get a negative 12. There's nothing in there that's going to give me negative 12. So it's not symmetric with respect to the x-axis. Again, 1 point can prove that it's not symmetric, but 1 point, so you can give a counterexample. Since that's not true, we know that it's not symmetric with the x-axis. All right, but if we got a true statement, we might have to work something else out. And I'll show you now here. If we were looking at a graph, we might think, well, I'm pretty sure it's symmetric to the y-axis, but we better check it out. All right, and again, the y-axis says if I plug in a value for x and then its negative value, I should get the same y values. Well, okay, so we picked 1 and we got 12, right? Well, let's pick negative 1, and do we get the same y value? So negative 1 to the 4th power is going to be a positive 1. Negative 1 squared is a positive 1, so that's plus 3, and plus 8 is 12. All right, so this is saying that there's a good chance that it's symmetric to the y-axis. Again, we said 1 point can't prove that. So let's look at this. F of a. If I plug in just a for x, I get a to the 4th plus 3a squared plus 8. And if it's symmetric to the y-axis, all right, we know that if we plug in negative a and get the same thing for y, so we'll get this same thing, we know it's symmetric. So if I go negative a to the fourth power plus 3 times negative a squared plus 8, if we get the same thing, it's symmetric. Okay? Well, negative a to the fourth power, anything to an even power is going to be positive, so we have a to the fourth. Plus negative a squared, well, anything to the positive power or even power is positive, so I have 3a squared plus 8. Is this are these two the same thing? Yep. Therefore, it's symmetric to the y-axis. All right. And the last example I have here, determine whether the graph of y times x equals 6 is symmetric in respect to the line y equal x and the line y equals negative x, neither or both. Here are our requirements for y equal to x and y equal to negative x. This is saying if I pick a value, if I pick a point 1, 2, then the point on the line also has to exist is 2, 1. It flips the x's and y's, and here over here it flips and it changes them negative. All right, but let's look at this. Check this out. So if I put a in for x and b in for y, I get a times b equals 6, right? If I switch that around and put b in for x and a in for y, we know that multiplication is commutative, correct? Like 2 times 3 is 6, and 3 times 2 is 6. It did not matter in which order I did it. These are equivalent things. Just like in that last problem, these are the same equations. Therefore, it's symmetric to the line y equal x. Well, we can do that same type of thing. If I plug in a for x and b for y, now we're looking at y equals a negative x line, that equals 6. Now what if we plug in negative b in for x times negative a in for y, because that's what our requirements say, equals 6. Are we going to get equivalent? Are those equal to each other? Well, a negative times a negative is always a positive. B times a equals 6 now, because a negative times a negative is a positive. And we just talked about how these are also the same thing because multiplication is commutative. So therefore, this is also symmetric to the line y equal to negative x. All right. So one last thing to talk about, even functions. Functions whose graphs are symmetric to with respect to the y-axis are even functions. If you looked at a lot of those, the best example I gave you is y equal x squared. That's an even function. All right, and that's symmetric to the y-axis. And odd functions, whose graphs are symmetric with respect to the origin. So if they ask you to tell you, if they ask if this function is even or odd, you need to find, if it's even, it has to be symmetric with respect to the x-axis. And if it's odd, it has to be symmetric with respect to the origin. Hope this helps. We'll see you in class.